Today, my talk will be on getting constraints on dark energy and like structure growth from CMB and from HIRAX and combining that with like CMB surveys. I'm a PhD student. I'm supervised by Professor Kaval Mudli. And this work we've been working in collaboration with Herda Prince, who's a PhD student, and a postdoc, Coralie Pennon. Most of us know that the cosmological paradigm at the moment is not well understood in terms of the energy budget, right? So like 95% of the energy distribution is just a mystery. So we don't know what these dark energy and dark matter components really are. So a lot of large scale structure surveys have been set up in the past few years, and that's planned for the future to try and better understand what these exotic matter distributions are and what is the cosmological model. So H1 surveys provide an exciting new tool because unlike conventional galaxy surveys, this can map large portions of the universe much quicker by not resolving individual galaxies. So we can get unprecedented measurements of the universe, and that can help us with, really get better constraints. So in this talk and in this work, we'll just look at one of those experiments that's set up to do this H1 survey called HIRAX, and how we can combine HIRAX with other large-scale structure surveys planned to get better constraints. Okay, so we know that the CMB measurements have already provided a wealth of information on constraining the cosmological models. And so we can see here from the CMB map, so that the early universe has these tiny thermal fluctuations which seed the large-scale structure matter distribution that we see today. So how do you get the statistics out of the CMB? So we use the 2-point correlation function, and this is actually the tool that we'll use in our analysis. The 2-point correlation function is quite simple to understand. It's like if you take a point in the map or the data set at some given location R, and we ask the question, what is the probability at some other point R point that there's also an overdensity if there is an overdensity at R. So we do this for all scales on the map for R and R prime combinations, and then we get the distribution of the clustering scales as a function of scale. And in the Fourier space, we call this the power spectrum. So in the plot in the lower half of the slide I show here is the CMB power spectrum from applying 2018 results. So the blue curve shows the theoretical model, and we see that the red points are the data set, and it fits really well with the cosmological model. And that helps us really get high precision measurements on what these model parameters are allowed to be. So we see in the CMB spectrum also the feature of the baryonic acoustic oscillation. So we see these acoustic peaks and these oscillations. So the location of these peaks and the heights of these peaks also tell us a lot about the cosmology and the density parameters in our cosmological model. So these baryonic acoustic oscillation is also an important tool that can be used to measure the cosmic expansion, as we'll see later on, which is what HIRAX is planning to do. But where does this baryonic acoustic oscillation or BAO scale or feature come from? So in the early universe, when the universe was much smaller, so we have the photons and the baryons were clustered together in a tight space. So it's behaved like a single fluid because the photons bounced off the electrons and protons, mainly the electrons. So we have this coupled fluid in the early universe with a photon pressure going outward and the inward gravitational pressure. But as time went, there's also the background cosmic expansion. So at a later time, the spaces between particles grew, the baryons, such that the photons could escape, and that's how we have the CMB. And when the CMB escaped this fluid, so now we say that the overdensities are frozen in because they no longer have the photon pressure. It's only the gravity and the background expansion. So this is a characteristic length scale in overdensities that's set by the sound speed of the fluid. And we can see that in this BAO rings image that I have here. So this is I guess the word is a much more pronounced or exaggerated view, but it shows that at some preferred length scale, there's more matter as you move outward from a position R. And this scale corresponds to about 150 megaparsecs. So we can use this preferred clustering scale in the density distribution as a standard ruler to measure cosmic history, much like how the supernova measurements we use as a standard candle. So galaxy surveys have also provided a lot of information on the large scale structure. So we can see here like the SDSS galaxy survey has mapped out this cosmic web, or the scaffolding of dark matter that holds the large scale structure. And again, we can get the statistics out of it. So we get the correlation function in real space now. So we can also see here that this preferred clustering scale. So in the real space, it shows up as just a bump in the correlation function, which shows the some evidence of the PAO feature also. Okay, so here I'm just showing, I guess the benefit of joining many data sets or many different measurements. So for example, on this plot here on the left, hopefully you can see my cursor. So we have the density parameters for dark energy and for matter, right? And we're showing, I guess, a few different probes of the large scale structure. So measuring just galaxy clusters or supernova or CMB measurements. And the point is where the data set is combined, right? Where you have this combined data set right at the middle. So you, by combining these data sets, you get a much tighter constraint on what the model parameters are allowed to be, right? And I show on the right these two much newer plots combining galaxy surveys with Planck CMB surveys and lensing surveys. So I guess, so we also see here the same thing where the combined data is, you get a much tighter constraint. But there's also this interesting feature whereby the early measurements of that measure the CMB, we see this tension between the early universe measurements and the late universe measurements. So one of the questions that's being asked is there something in the physics of the early universe compared to the late universe? Or is there something systematic in the experiments? And that's where much more data sets would help us. So for example, if we have a H1 measurement on this, what would it do? Does that support the CMB measurements, or does it support the galaxy surveys, etc., or does it show something totally different also? So that's why combining data sets are important. Okay, so what is the H1 intensity mappings in that case? So H1 intensity mapping maps the neutral hydrogen in the universe, which is the most abundant element. So neutral hydrogen undergoes the spin flip transition, whereby the single electron can flip to a lower energy state and release a characteristic 21 centimeter line emission. It is a weak signal, but given and the transition is not is an unfavorable transition. But given the abundance of H1, we do expect to make a good measurement, just based on the statistical nature of the abundance of H1. Okay, so what we can do is we can also get the large scale structure as seen in this simulation distribution here of the dark matter distribution and the scaffolding of large scale structure from H1, right? Because H1 is also following the distribution of gravity and dark matter. So we can, in fact, also get this 3D map of the universe, like the CMB maps, but in this case, it's per redshift because we're measuring the spectral line. So we can get a 3D map of the universe at all different redshift slices. But one of the challenges facing these H1 experiments is that the foregrounds, mainly the galactic foregrounds, but also extragalactic point sources, are higher in amplitude or is much brighter than the cosmological 21 centimeter signal. So we can see that in this plot on the right. So the blue curve shows the signal of the 21 centimeter, and the red is different components of the foreground. So we can see that the foregrounds are much brighter than the cosmological signal. So one of the things we can do, however, in trying to remove this foreground is by the knowledge that the foregrounds are slowly varying in frequency, right? And the cosmological signal is thought to be oscillating. So you can do a component separation by going into the Fourier space, because the slowly varying foregrounds will be contained at much lower Fourier modes than the cosmological signal. Okay, so the HIRAX experiment is designed to measure neutral hydrogen in the universe. So it will be a 1024 6-meter interferometer array that will be located in the Kourou site, and it will operate in the 400 to 800 megahertz frequency range. So the HIRAX will measure the neutral hydrogen. So this 400 to 800 megahertz corresponds to about 11 billion to 7 billion years ago. So it will measure the neutral hydrogen at a time when the universe starts to be dominated by dark energy, right? So in other words, when dark energy starts to dominate the expansion history, that's the exact time we're trying to measure the neutral hydrogen and try and get the baryonic acoustic oscillation figure feature as it's evolving in time. Okay, so how do we model the H1 signal to do these forecasts? So firstly, we say that the H1 signal is a biased tracer of the matter density. So then we just say it follows the matter density contrast here with where K corresponds to scales with some bias. But we also have to add a correction term for the RSD, so the retrospace distortions, which is characterized by this F mu K squared term. And here F is one of these growth parameters. So it's the linear growth function, and it's used to characterize the growth of structures in different models. And we multiply that by a mean brightness temperature to get a thermal fluctuation of the 21 centimeter line. So here we can compute the power spectrum by doing this 2-point correlation function at different scales, L and L prime, to get the 21 centimeter power spectrum as a function of L. But with any experiment, there's always uncertainty or I guess noise in the sense of interferometers. We have the interferometric noise that's defined by this equation in the bottom. So that depends on the system temperature, the field of view. So basically the parameters of the instrument, the total time of the instrument, and this N of view function, which is the baseline density function. So a baseline is the separation of two dishes in an interferometer. So if you have an interferometer laid out in a specific way, then you have a specific baseline density function. Okay, so here I show the plots of the 21 centimeter power spectrum when we compute it this way and calculate it. And in blue, I show the noise, thermal noise for HIRAX. So we can see from this plot that HIRAX is designed to specifically minimize the noise in the scales of where the BAO is most prominent. So you can see these wiggles in the power spectrum, which is shown by these colored lines. So where these features oscillate is where the BAO is expected to be. And we can see that HIRAX minimizes the noise there. And on the right, I show a signal to noise ratio in one redshift bin. So we can see it's about the order of 50 in each pixel, or peaks at 50 in this pixel, which is quite high signal to noise, which we can use to get good parameter constraints, which we'll see later. Okay, so why do cross-correlation science then? So cross-correlation surveys can help improve individual survey measurements, or improve on rather, by minimizing systematics that show up in the individual surveys that won't be there when you combine them. In fact, the first detection of H1 was actually made in a cross-correlation survey of the Green Bank telescope and the Deep 2 optical telescope, as can be seen in this paper, Chang et al. 2010. Also, HIRAX will have good redshift overlap with many next generation cosmological surveys, such as photometric galaxy surveys like DES and LSST, spectroscopic galaxy surveys like DESI, Euclid, WFIRST, and Roman. So we've also done some insurer work on LSST and HIRAX cross correlation. So Momita is actually leading that work, and we've started some Roman HIRAX cross correlations also that we're looking at. In this case specifically, we look at the CMB survey, specifically CMB lensing surveys of an advanced ACT-like telescope. Okay, so we consider here the CMB lensing case, and so the statistic or the field that we choose to probe the CMB lensing is called the convergence field, right? So how does the CMB lensing trace the large-scale structure distribution? So we can see in this image that the CMB photons do not come to us unimpeded, right? They have to pass the entire large-scale distribution of the universe. So the deflections of this large-scale cosmic structure shows up in the CMB that we measure today, right? It's the lensed measurement. So the lensing in some way has information about the large-scale structure, right? And we can code that in this convergence convergence signal here. So in real space, the convergence is basically saying it is the integrated matter density along the line of sight with some weighting kernel. And the weighting kernel depends on the cosmology. Okay, so how do we compute this cross correlation? So in the same way like we did the H1 case, we do a 2-point correlation function. So we take a 21 centimeter field and we correlate it with the convergence field at different scales, and we get the cross correlation power spectrum. So I show this in this first plot here. So the thing we can see here is when we have the cross correlation signal, which is the total signal, which is shown in blue, when we don't do any mode subtraction. So basically it's all the modes or scales accessible by the experiments. Then we have some signal here. But the thing to note in the cross correlation is when you start removing K parallel modes or radial modes, we lose a lot of signal really quick, right? And why we do this is because for the foreground subtraction, like I mentioned, we effectively cut K parallel modes, or we lose radial modes up to about 0.1 megaparsec inverse, right? So we can see that it drops by a lot of orders of magnitude, and especially by the time we get to the foreground cut, it's down by about 6 orders of magnitude. And the reason for that is that kernel that I spoke of earlier, the weighting kernel for the CMB, falls off sharply as a function of K parallel. So you can see also in terms of a signal to noise, so when there's all of the modes considered, we have a peak signal to noise summed over cumulatively to be about 10, right, which is some detection. But by the time we do this foreground subtraction, it basically is all gone, right? But it turns out that we can recover a signal in this correlation by going to a higher order statistic. So we compute the 3-point function bispectrum. So what we do here is we take two 21 centimeter modes and we correlate it with a background convergence field, right? So what we're doing here is taking advantage of this density modulation effect. So if you can think of, so this little schematic here. So the bright background color and the dark background color is high density and low density background fields, which is probed by the convergence. And this blue stars is the small scale fluctuations probed by the 21 centimeter line. So where there is a brighter or higher density in the background, you have more clustering or more signal of more correlation of the 21 centimeter field. And where there's a low background mode, then you also have less clustering of the 21 centimeter field. So that's the signal we probe in the bispectrum. But we also have a bispectrum uncertainty, and that's defined by the variance of the bispectrum. So we take like effectively the 6-point function. So we correlate each field with itself at a different, from the bispectrum with a different scale or at a different scale. And so I show the plot here of the bispectrum signal versus the effective variance or the dominant term in the bispectrum variance, right? And we show that for different y values, which corresponds to K parallel. And what we can see is that if we convert this to a signal to noise estimate in a single redshift bin, so the peak now is about 20 in each of these pixels, right? And this is after the foreground modes have been cut. So that's a quite significant boost compared to just the 2-point function. So we have really high signal to noise in both the H1 auto and the bispectrum with the CMB lensing case. We can convert this to a constraints. So to obtain parameter constraints, what we use is the Fischer forecasting analysis method. So basically what this does is it's based on a likelihood estimator, whereby if you're given some measurement or some data set, what is the probable, or how well can we constrain a model given some data, right? And how we calculate the Fischer matrix is shown here on this top equation. So the Fischer matrix is basically dependent on the modes you're accessible to. So the survey area times this delta nu. This is like a mode volume area, mode volume factor, right? And how sensitive your probe is. So X total is the probe. So it's either the bispectrum or the 21 centimeter power spectrum, right? The signal plus the noise. So how sensitive this probe is to your parameters, so alpha, beta parameters, right? So you take the derivative of the signals. So you're basically probing how sensitive these signals are to a parameter, and you're summing, and the integrals are just summing over all the modes. So that's how we get our Fischer matrix for the parameter constraints, right? And then, so basically, firstly, that gives us the basic parameters. So for example, in the H1 case, the basic parameters we've seen were the bias, the F function, the amplitude of the power spectrum. But if we want cosmological parameters, that's more implicit parameters. We can get that by defining this distance scale parameters, alpha perp and alpha parallel, which is just the angular diameter distance and the Hubble parameter. And implicitly defined in these functions are the cosmological parameters and the dark energy parameters, etc. And then we do this transformation of a Fischer matrix from the basic parameters to the extended list, which has the basic parameters plus the cosmological parameters, by multiplying with the transformation matrix, which is a derivative of the old parameters with respect to the new parameters. So basically, it's going from Fischer matrix with which basically has the functions f, a perp, a parallel, marginalized over the bias, and etc., to a new parameter, a new Fischer matrix, which has the cosmological parameters, the density contrast of dark energy, of curvature, dark energy equation of state, H and gamma. Okay, so here I show the results for the basic parameter constraints. So here we can see the baryonic acoustic oscillation amplitude, the sigma 8, which is like the power spectrum amplitude, the H1 bias in first order and second order, and the linear growth function f. Omega H1 is the H1 density contrast. So we've included that as a degenerate parameter would be and f. Yeah, in terms of structure growth, the important thing is the power spectrum amplitude sigma 8 and f, right? So those are two parameters that can tell you about structure growth. So here we see, in general, H1 surveys don't independently measure this, and neither does the bispectrum measure it well. But by combining the red and the orange, so the bispectrum and the 21 centimeter autocorrelation, we get the blue curve, right? That's the sum. And that basically constrains each of these parameters really well, where in the case where the individual probes don't. The cosmological parameters also, we get really good constraints. We add the Planck trier here. So the H1 for HIRAX on its own does quite well on most of these parameters, specifically the dark energy cases. But we can see that in this case, when we add also the orange curve, which is the bispectrum, we do get the red curve, which is much better. We do improve on the H1 alone survey. So I guess the summary for the constraints is that the structure growth models F and sigma 8, which you can use to tell different dark energy model, modified gravity models, and different cosmological structure growth models, we get this really tight constraint, and we break the degeneracy. And in terms of dark energy, so HIRAX on its own does really well. It's about 370 dark energy figure of merit, which is not that far off from SKA phase 1, but combined it goes really much higher than that, almost 900, which is a really competitive constraint on the dark energy equation of state parameters. Yeah, so I guess to conclude, so next generation experiments will provide much greater information on the nature of the universe, and we can combine these surveys to place even higher constraints on the cosmological model. We showed how HIRAX can be used with the next generation experiments, specifically your CMB lensing, to put competitive constraints on dark energy and structure growth parameters. So for future work, we'll also look at constraining specific modified gravity models. And also we would want to do extended models such as like, can we constrain neutrino masses, non-Gaussianity parameters, or like scale dependent biases. We'll also advancing the galaxy survey models. I didn't write that here. So the galaxy HIRAX cross correlations, and trying to get applications for those and constraints from those. I guess that's the end of my talk. Thank you for your attention.
Thanks, Warren. That was a very interesting talk. I have maybe a minute or two for questions. Do you know what the current status is of H1 auto correlation, like detecting the H1 signal in the autocorrelation? Do you know if this has been done yet?
Yeah, it hasn't been done yet, as far as I know. I guess that's the race for the autocorrelation intensity mapping detection is the thing at the moment.
That's why we're all working so hard.
Yeah. Okay. So it's a race to the finish, I guess. And another question I had was when you construct this cross correlation power spectrum, you had a quick slide of how you construct that. Is it like, do you multiply it in the multipole space, or do you like multiply kappa maps with 21 centimeter maps and then take the multipoles? Or
no,
which way around?
We do it in the multipole space. So you mean in the L space, right?
Yeah.
So we do this correlation in the L space, theoretically.
Which amounts to just multiplying the two power spectra together, is that right? Or, I mean,
yes.
Like, okay.
Yeah, I think so.
I think you have to actually filter the Kappa map. There's a paper that describes this in more detail, but yeah, you basically want to work out the average density in patches on the sky, the average lensing field, and then you cross-correlate that with the 21 centimeter maps. Yeah.
Okay.
Yeah. So you do it in a patch by patch kind of way.
Oh, okay. Cool. Thanks. I see Cabello has his hand up. Cabello, you want to go ahead?
Thank you so much for a beautiful talk, Aaron. So I just like one of the first questions that I wanted to ask was like, what's worse between the extragalactic and the galactic foregrounds? Do you observe them as like one thing or are they separate? And do you mind like going over how you actually separate the foreground from the data?
Yeah, so for H1, definitely the galaxy is the worst component. I guess in terms of removing them, so in our case here, in the analytical case, so since the foreground is slowly varying in frequency space, right? And the cosmological signal is rapidly oscillating in the frequency space. So when you Fourier transform that, it corresponds to um, the foreground having most of its power on a low Fourier mode. And the cosmological signal is on does have some power on low Fourier modes, but mostly on high Fourier modes, right? Because of the oscillatory nature. This is like spectral analysis or signal analysis. And so if you remove those low Fourier modes where the foreground is dominating, you can effectively get rid of the foregrounds and have only, well, mainly a signal left. Does that answer your question?
Yeah. And I also wanted to ask about the bias. I usually hear people talking about the bias on the modeling of the H1 signal equation. What's this bias and like what really determines its value?
Yeah, so that's a good question. So the bias is, so we don't necessarily think that the H1 follows the matter density or the dark matter perfectly, right? Just a simple example, like at some point when nonlinear scales take in, you get this lot of I guess active galactic nuclei things, and then in some cases that can cause neutral hydrogen to be ionized, for example, right? So there's a lot of processes in general that may not make this a perfect linear relationship, right? So there has to be some multiplicative factor that can depend on redshift, but also scale. But in this case, we ignore scale that deviates from being a perfect tracer. So what determines this H1 bias is a good question, because so firstly we model it using like halo model statistics, right? So there's calculations done based on the evolution equations and then the halo models, and then you get this long bias terms and then higher order corrections. But in terms of measurements, I guess you can use measurements to constrain the biases. So that's the thing that we have also argued in this work with your constraint from the bias can be. And if you have many different measurements, then you can have different constraints. So then you can get like a combined constraint on. So if you can measure H1 in many different surveys too.
Okay, thank you.
Yeah, just to add to that first part, Warren, for the BAOs, because they're on such large scales, I think the galactic foregrounds are a problem. But if you go to smaller scales, there's clustering. The extragalactic sources can be a problem if you're trying to do like these cross correlations, etc., because they are sitting in halos. So, and the signal from the 21 centimeter is also sitting in halos. So if you're trying to probe halos, then the extragalactic, as opposed to the BAOs, which are on much larger scales, then the extragalactic component can be a problem. So so that's something worth noting of the foregrounds. So basically the AGN, signal from in the halos can be a problem for cross correlation.
Is that something you would just mask out, or like you remove it in K-space somewhere?
Yeah, I think the hope would be you filter it out in the same way you filter the galactic foregrounds as well, a smooth spectra. So,
okay.
Yeah, but it remains to be seen.
Right.
As does the galactic filtering. So,
well, if we don't have any more questions, I think we can thank Warren once again. Thanks, Warren.